Okay, we're going to start going, excuse me, allergies, going through the part 1 of the spring final exam review. So if you actually looked at the chapters in the book, these are over chapters 5 and 6, primarily binomial distributions and probabilities. So actually, I guess I should turn off my key. Let me do that. Now it's going to give me different numbers, but that's fine. We can do it. Okay. And I do have this Google Jamboard here filled in with some of the things that might be handy on this particular review. Okay, so let's get started with this one. So I went ahead and we're talking about binomial distribution. So that's really the first part of your review. You need to have exactly 2 outcomes, not 3. So make sure you check that box. Probability of success should not change. It should be the same on every trial. And the trials are independent. They need to be independent. And a fixed number of repeated trials under identical conditions. So that should be the 4 that you need to check on that problem. Excuse me. And there you go. And I do have these listed right here. Trials have exactly 2 outcomes. They're independent. Probability of success is the same, and a fixed number of trials under identical conditions. So for a binomial probability distribution, it is unusual for the number of successes to be less than more than 2.5 standard deviations away from your mean. That's what that mean minus 2.5 sigma. So that's what this means right here. Okay, so you go 2.5 standard deviations below your mean, and it's also unusual to be higher than 2.5 standard deviations above your mean. So for a binomial experiment with 10 trials, for which the probability of success is 0.2, is it unusual to have more than 5 successes? So what I would do is I would actually go ahead and, let me go ahead and do a binomial distribution. So you do the staplet. Oops, pretend I did staplet. There we go. And we're doing binomial distributions. The reason I'm doing this is it will actually calculate your mean and your standard deviation. So 10 and p is 0.2. And that's what it looks like. So if I go more than 2.5 away of these, then that would be unusual. So my mean is 2. 2.5 of these is, let's see, so I would have 2.4 plus 0.6, roughly 5. So yes, is 5. Let's double check that. Let's do the math. Here's an easy way to do it. All right, so you go to normal distributions. All right, and we'll go to staplet again. I'm going to do normal distributions. My mean, let me pull up my mean is 2, and my standard deviation is 1.2649. So you put 2, 1.2649, and plot the distribution and figure out what is unusual there. So 2.5 standard deviations. I can't really do it on here, can I? Let's see. Let me go back to my other normal. So 2.5 standard deviations, that would be that. I'm actually going to have to do some math. So let me go ahead and put up a calculator. Poor Mrs. Overman, she needs to use a calculator. TechSmith, and not TechSmith, TI SmartView. All right, so I'll pull up the calculator, and what I'm going to do is figure out what 2.5 standard deviations is, all right? Because it's between 5 and 6, I can tell you that. So I'll go 2.5 times, and my standard deviation is 1.2649, and add that to my mean, which is 2. So it's about 5.166, 16225. Is 5, well, that's close. So more than 5 successes, I would say it's close to 5. It's really close to 5. It might want to say 6, but I would say it's really close to 5, okay, because it's a little bit over 5. That's the issue. So let's hit submit, see if I get dinged on this one. Yep, that's it. It's very close to 5, so they were very happy with that number right there. So what I did is I took the standard deviation times 2.5, and then I added it to the mean. So basically, that would be on the Jamboard. I basically did this calculation right here. I said mean, which is 2, plus 2.5 times your sigma, which was 1.2649. Okay, so we got that one right. If you were simply guessing on a multiple choice exam consisting of 10 questions with 5 possible answers, so that's kind of the same situation here, would you be likely to get more than half the questions correct? Explain. So more than half, let's go to a binomial distribution, which I already had set up. There's 10 and there's 0.2. Half of them would be more than, they said half. Half would be 5, right? Hit go. And you could see that the probability is actually pretty low. It's 0.0064. So I'm using the binomial distribution where there are 10 trials and p is 0.2. I plot the distribution, and then I said, okay, probability of more than 5, go, and that's all these areas right here. So it appears to be very small. So I don't need this calculator. Let me move it out of the way. So the probability that it's greater than 5 is very small, so it'd be unlikely to get more than half the questions correct. And that should be right. I don't know if you can hear the birds outside. Whoa. I haven't answered that one. Oh, I forgot to answer that one, but I got that one right. Okay. What does the random variable of a binomial experiment measure? Basically, the number of successes in n trials. So like here, if you look at the binomial distribution, here are the measurements. 0 successes, 1, 2, 3, 4, 5, 6. So let's go ahead and make sure that Mrs. Overman got that right. And voila. Okay, so now we're good on those two. Consider a binomial experiment. If the number of trials is increased, what happens to the expected value and to the standard deviation? So we're going to go ahead. Currently, we have 10 trials. I might as well use this. So currently, the mean is 2, and that's 1.264. So let's do 20. So all I'm doing is doing trials. So now the mean is 4, and the standard deviation went up. So both will increase. All right. That's an easy way to test. Just put in a bigger number. There you go. All right. Now we have a Consumer Bankers Association released a report showing the lengths of automobile leases for new automobiles. The results are as follows. Use the midpoint of each class and call the midpoint of the last class 66.5 months for purposes of computing the expected lease term. So the distribution you're really going to want is called the discrete random variable. And what we're doing, if you look at my Staplet here, let me go to the next slide. Here you go. What you need to do is actually go calculate the midpoint. So here I did 13 plus 24 divided by 2. And then that gave me 18.5. And what I do is I go to the discrete random variable Staplet. Let's go to that one. Let me change input so you can see it. So we've got 13 plus 24 divided by 2 is 18.5, and then I have 30.5 for 25 plus 36. Just because it looks like a minus sign in there doesn't mean you're subtracting. You have to add these two, then divide by 2 to get the midpoints. Once you get all the midpoints, you can put in all the relative frequencies, and you can see them all here. Hit Begin Analysis, and believe it or not, it gives you your mean right here on the bottom. So I can say 36.884. Hopefully it won't ding me since I did 3 decimals. And then the standard deviation is 11.1347. So I just get them from the summary statistics on bottom. So the main idea is you set up your table. The Staplet you want is this one right here, discrete random variables, when it gives you a table like that, okay? So you will end up setting up this table with all the midpoints, and you put in all the probabilities. Okay, then they said sketch a graph. Guess what? We've got a rough graph here. This one might be it. Let's go ahead and look. Might have to slide here. Let's see. Yeah, none of the others look right. It has to be this one. And I'll go ahead and hit enter. Submit for testing. And looks like I got that one right. Okay, we're going to do another discrete random variable where I'm going to have to do midpoint. So I'll just duplicate this. All right, create another table. So that's what it looks like when you start with it. So For each age group, compute the probability that the moose in that age group is killed by a wolf. Round your answers to 3 decimal places. So I think we're just going to use the 0.5 years here because we don't have really a range. Now this part's going to get a little tricky. So let me first go up here and add in all my values. 1 to 5, that's a midpoint of 3. And then we have 6 to 10, that's a midpoint of 8. 11 to 15 is a midpoint of 13. And then 16 to 20 is a midpoint of 18. All right. Now we know that there are 296 moose deaths. So I could add these up, but I don't have to. So what I'm going to have to do is go 111 divided by 296. So that's 0.375. So I'm going to put 0.375. I pretend I can put in 0.375. 0.375. All right. Now I'm going to come back to my calculator. See, there's the 0.375. All right. I'll just put it right there. Kind of hard to see, but it should work. Won't go any smaller, will it? Oh, maybe it will. All right. Then we have 45 divided by 296. You're all divided by 296. And I get a really ugly number, 0.15. Let me make that a little big. 152. 0.152. Then I have to do, let's see how many for this next one. 74 divided by 296. So you will probably want a calculator for this part, 0.25. And then we have 61 divided by 296. And I'm getting 0.206. Okay. And then finally 5 divided by 296. And, oh, what was that? 0.017. Let's hopefully that works. Yes, so they all added up, so we're good. If I had been off on one of these, let's say I accidentally did 0.17 instead. Okay, that's fine. If I did that, it's going to say, oh, there's some problem because they don't add up to 1. So make sure, they will double check it to make sure it adds up to 1. Okay, so I created my thing. Now, that gives me the mean and standard deviation, so I can just type those down here. 5.6275. 5.1103. For each age group, compute the probability that a moose in that age group is killed by a wolf. Oh, guess what? That's these. So I just have to take my answers over here, 0.375. Oh, pretend I put in the right answers. 0.250, 0.206, 0.017. So we'll go ahead and submit all that. And there you go. Whole problem's done. So part of this was actually calculating the probabilities that go into this table that you're going to need anyways. And if you put this in the Statlet under discrete random variables, remember when you have these tables here, it's discrete random variables like this. You scroll to the bottom and it gives you the mean and standard deviation. Now this one I don't have a table, so it's probably not a discrete random variable. It's probably a binomial distribution. So let's see, 60% of auto insurance claims submitted for property damage were submitted by males under 25. So that's probably my 0.6, my P, 0.6. And we select 10. Okay, that's that. So I'm going to hit plot distribution. Okay. And then they say, oh, which one of these is the graph? I'm going to say that's the graph right there. That looks the most like it, right? Yeah, because this is a little lower. No reason to think it'll be different. Hit submit just to be safe. Voila. What is the probability that 2 or more? That means at least 2. And hit go. Or I could have also said from 2 to 10. That would have also worked. So my probability you can see is 0.9983. If I went like that, I still get 0.9983. And then right above it, you have the mean, which is 6. And your standard deviation is 1.54. Pretend I can put the right numbers. 1.5492. So when you have the staplet, that makes these problems super easy. The main thing is understanding at least, at most, this less than, greater than. In fact, I was just on a Facebook tiff. There was a hot take saying shit about alligators. You know how Mrs. Overman feels about alligators. It's a disservice to you. All right, so we got 15 pens selected randomly. So that sounds like 15 is in. What percentage is defective? So we have 10% are defective, so I'll put 0.10. All right, so that's defective. Remember what they said, okay? 10% are defective. Find the probability of the shipment if 10% of the total shipment is defective. So they've select 15 randomly pens, and you can't have no more than 2 defective. So no more than 2 means you can have at most 2 defective, right? You can have at most 2. Or if you weren't so comfortable, you could say you have anywhere from 0 to 2, right? That would also work, and that would give you 0.8159 is your probability right there. So from 0 to 2 pens, having them defective, 81.59% of the time, your shipment should be accepted. So now we're going to change it. It's not 10% anymore. It's 20% are defective, all right? Still 15 pens, though. And we're still dealing with the 0 to 2. And now we can see, because more of the shipment is defective, it's more likely we're going to reject it. So we only have a 39.8% chance that the shipment is accepted. All right, so we had N is 15, and the second part, P is 0.2, because 20% is 0.2. And we just need to have 2 or less defective, and we accept the shipment. All right, and come down, submit for testing. Oops, wait. Oh, you got to pay attention to that. Not accepted. So that means 3 to 14. Or you could say at least 3. That's the easiest. 3, pretend I can hit the right keys. 0.602, it's a complement. See, I was sort of reading it, but I wasn't reading it. That said not accepted, right? So pay attention to that. If you miss it, luckily you get another shot and you can go, oh, it said not accepted. I'm just modeling for you. No, I actually did make that mistake. That was not on purpose, but it's a good, happy mistake. All right, according to Harper's Index, 55%, oh, I bet you that's the P, 0.55, of all federal inmates are serving time for drug dealing. We take a random sample of 20, plot distribution. What is the probability? 13 or more. So that means at least 13. Go. 25.2% or 0.252. What is the probability? 2 or fewer? At most 2. 0 pretty much. I'll just do 0 here. Okay. What is the expected number of inmates serving time for drug dealing? It's right there, the mean, it's 11. All right, hopefully that 0 is not messing us up. Let's see. Should be just fine. Yep, there you go. Okay, on to problem 9. 84% of flights. So I'm going to put 0.84. I'm pretty sure that's what I need. May not. And we're considering a random sample of 202 flights. Ooh, look at that. Wow, very big. What is the expected number that will arrive on time? Oh, I just have to do this. 169.68. What is the standard deviation? 5.2105. That's it. Scroll. This staplet is like totally life-saving here. It does so much work for you. You don't have to think very hard. And there it is. Voila. Okay, 80% of a grapefruit crop is good. Okay, so we're going to assume good. I might have to change it to bad. We'll see. And grapefruits are sold in sacks of 10. So there are 10 grapefruits per bag. Let R be the number of good grapefruits. So we do want the 0.8. So most of the time we're going to have a high number of good grapefruit. And that kind of looks like this distribution here. All right. What is the probability of getting no more than 1 bad grapefruit? So at most, 1, right? So no more than 1 bad means 0 and 1. So you could do it this way, right? By the way, that's 0. Or you can go 0 and 1, go. Oh, these are good grapefruits. Bad grapefruit, bad grapefruit. Think, think, think. Probability for bad grapefruit. I'm going to change it to probability for bad grapefruit. Now it makes sense. Okay, so probability of 0 or 1, at most 1, we go, and it's 0.3758. If you don't like that at most 1, you can say between 0 and 1. Say, oh, that feels more comfortable for me. And you should get exactly the same answer you do. What is the probability of getting at least 1 good grapefruit? Let me change this to good, because then I'm working in the same words as my problem. At least 1 great, good. At least 1. Good grapefruit, it's probably about 100%. It is, all right. What is the expected number of good grapefruit? See, this is why it's good that I changed it to good. We should have about 8 good grapefruits, and our standard deviation is 1.2649. Pay attention to the words and adjust the numbers, and then it gets easier. There we go. We're all done with the grapefruit. Okay, Orchard Cafe has 15% of people who make reservations don't show up. So those are the ones that don't show up. I might have to change that to the complement. We'll see. We have 81 reservations. These are people not showing up. How many can be expected to show up? So I actually have the wrong P. I want the probability for people showing up, not the probability for people not showing up. So the expected number is 68.85. And my standard deviation is 3.2136. So it's okay to put the numbers in right as you read them, as long as you realize you might have to change them to better reflect the wording of the question. And everything's good. We're beautiful. Student government claims 80% of students favor an increase in something. Student fees. And we do a sample of 8. So these are people in favor. What is probability 2 or fewer will favor? So that means at most 2, or you could go 0 to 2 down here, right? And that's pretty tiny, 0.0012. Does the data support the government's claim, or does it seem the percentage favoring the increase is less than 80%? So let's see, a random sample produced 2 in favor. We would say no, because this probability is pretty low that we would get that. So the data seems to indicate that it's actually lower than the 80%, because we're kind of in the unusual territory right there. Kind of a hint of the inference that we would get to later this semester when we said, oh, the probability of getting this sample as small or smaller, that would give us the p-value. And that's what we just calculated right there. Right there. Voila. Okay. On to question 13. Look, we're over halfway through. Okay, so I do have a card for this. It should be card 3. Remember that AC, you can't see it very well, as a complement or the opposite of A, so it does not own a cell phone. So you would take A and put a not in there. Okay. A and B means both of these are true, owns a cell phone and a laptop. There we go. And A or B owns a cell phone or a laptop. A given B owns a cell phone given that they own a laptop. There we go. B given A owns a laptop. Make sure I have the right B. Given they own a cell phone. Oh, not does not. Owns a laptop given they own a cell phone. Go ahead and check those answers. We're moving along. There they go. They're all right. Yay. All correct. Okay. You are given the information probability of A equals 30 and probability of B equals 0.4. Do you have information to compute probability of A or B? Well, technically, probability of A or B, that's this one right here, is probability of A plus probability of B minus the probability of A and B. So we need to know that value. All right. If we know they're exclusive, then this is 0, and we can just add them, all right? So we'd say it's 0.3, A or B, it should be 0.7, right? Oh, wait, this says and B. Why does that say or? That looks like that should say and. Oh, wait, here we go. If you know that's A and B are mutually exclusive, do you have enough information to compute probability of A or B? Actually, don't. That does not provide any extra information. We needed to know they were independent before I could say that was. Let's see, that could be wrong. Let me double check that one. Mrs. Everman's doing a double take on it. Let's go see. Let's go see. Okay. If you know the events A and B are mutually, do you have enough information to A or B? It should just be the and. Why did he say and? Oh, and it equals 0. Oh, here we go. There we go. Remember, that's what I was kind of saying. So this is 0 if they're exclusive, so we just know that it's these two added together. There we go. There was a reason I was kind of double taking on that one. I was confused because there was ands in there, and I was like, but we're looking for or. Read carefully. Even Mrs. Overman has to do that. So there you go. All right, you're given the probability of A is 0.3 and probability of B is 0.4. Do you have enough to compute A and B? You have to know if they're independent, all right? So if they are, then yes, you could just multiply it. If you know they're independent, then you just multiply, which would just be yes for independent events, multiply. That's it, all right? I probably should add that. In fact, while it's grading, let me go ahead and, come on. Let me delete that. And provided that A and B are independent. So that'll help for that slide right there. So you can multiply them if you know that they are independent. And there you go. We're all good. For a class activity, your group has been assigned the task of generating a quiz question that requires use of the formula for conditional probability to compute probability of B given A. If your group comes up with the following question, if probability of A and B is 0.4 and probability of A is 0.2, what is the probability of B given A? Well, believe it or not, probability of A should always be greater than the probability of A and B, okay? So that's supposed to say note. So this cannot happen. Probability of A and B cannot be greater than probability of A, all right? So it's just a weirdness, all right? And it's actually going to give you an answer greater than 1, usually, if that were true. Okay, so you would get an answer greater than 1. We'll say or, which is not possible, right? So it's not possible, so let's go ahead and go that. Submit. And it agrees. You can't get a probability bigger than 1. Okay, does it pay to ask for a raise? According to the survey of the women interviewed, 24% had asked for a raise, and of those, 45% received it. If a woman is selected at random from the survey population of women, find the following probabilities. Probability they asked for a raise was 24, right? The probability she got a raise if she asked was 0.45. Now what you need to do is just multiply those two numbers together, because basically what I'm using is probability of A and B. You just multiply it. Now you're probably going, wait a second, they're not independent. Well, you can kind of say, you can do this, really. Note, probability of B given A equals probability of B if A and B are independent. That's probably a good way of putting it. So we can just multiply these two numbers together. And so I'm going to go 0.24 times 0.45. Make sure you do decimals, don't do percents, it won't work. 0.106, I think. 0.108. That's kind of small, I know, I apologize. And we'll submit this. We're almost done. Oh, look at that, we're almost there. not as bad as you thought. It looks like a long review, I know. This is probably pretty rusty for you because this is beginning of the semester. Okay, same thing. Does it pay to ask for a raise? According to survey, men interviewed, 15% had asked for a raise, 62% who asked for it received it. Same exact question, right? So probability a man asked for a raise is 0.15. If probability is 0.62 that he received it if he asked for it. Doesn't seem fair. And then this one is exactly the same situation. We do 0.15 times 0.62. And we get 0.093. So the men weren't as good about asking for a raise, but they were better about getting it when they did ask for it. It's random numbers, so we don't know. These are just made-up problems. You don't have to get agitated. All right. Then, okay, drop a thumbtack and observe how it lands. Describe how you could use a relative frequency to estimate the probability a thumbtack will land with its flat side down. So you count the number of times the tack lands flat side down. That sounds really good. And then you divide by the total number of times dropped. Let's see. Point down. We don't want point down. We want flat side down, right? Yes. And then, no, this one's too complicated. What is the sample space of outcomes for the thumbtack? Down and up? Not really left and right. How would you make a probability assignment for this sample? For if when you drop 500 tacks, 355 land flat side down. So what we could do, by the way, here's a nice trick. You can say flat side down is 355. So if you want to do the math, I'll do it for you here. 500 minus 355 is 145. So 145 landed flat side, tack, pointy side up, right? Flat side down, flat side up, whatever. Okay, out of 500, flat side down is 355. Look, you can do the fractions. That's the nice thing about WebAssign. You don't have to divide it out. Of course, watch it show me wrong. It won't. This should be fine. There you go. Told you. Look, you can do that. You don't even have to divide. Okay, one of our last but not least problems. Look how close we are. Okay, let's use the following notation. This is the one where they get exposed to poison ivy, and within 5 minutes, if they wash, within 5 minutes, if they wash after 5 minutes. So let's see where they wash the oil off, right? So what's the probability of no reaction? So that's just no reaction total. So that's 470 divided by 1,000. Probability of a mild reaction is 399 divided by 1,000. Probability of a strong reaction is 131 divided by 1,000. And by the way, if you do the fractions, this should work here. Probability of no reaction if it was within 5 minutes. So that's 406 have no reaction out of 500. Okay. Then strong reaction is there are 39 out of 500. Probability of no reaction if they waited 5 minutes, there were 64 only out of 500. And strong reaction, there were actually 92 out of 500. Probability of no reaction and within 5 minutes, there were 406 of those out of the total. It's not a given. So when you have the givens, that means I was just in this column right here, right? This column right there. For the given W. Given A means I'm only in this column. If I don't have those vertical lines, then I really have to use the total. So you can see it's 500 here, here, and there, but these are using 1,000. Probability of mild and within 5 minutes, there were 55 of those out of 1,000. All right, let's go ahead and check our work so far. So far, so good. See, I told you could do decimals. Now, here's the tricky one. No reaction or mild reaction. So this is actually not too bad. So I'm just going to have the 470 plus the 399. There's no overlap, so I don't have to divide anything out. I can just go 869 divided by 1,000. Are the events no reaction and mild reaction mutually exclusive? Yes, because they can't happen at the same time, right? You can't have no reaction and a mild reaction. You got one or the other. Are the events no reaction and W washing off within 5 minutes independent? Should not be, because basically the probability of no reaction is 0.47, right? The probability of within is 50-50, right? And then if I said, what was it, no reaction, if I go 405 divided by 1,000, that is the probability of no reaction and with washing the oil off. So that's the N and the W, all right? So we can't just multiply them, they're dependent. You can see that no reaction depends on which column you're in. So I'm gonna say you just cannot multiply them, it won't work, right? Whoops, not yes, it should say no. They're not independent. We'll hit submit. And you can see it in the columns. It's like, you really want to wash that oil off within 5 minutes if you don't want a reaction, right? And there you go. We've got all the right answers. So we're down to the last few. Let's see how many of these we can knock out. Class records indicate a student selected at random has a probability of 0.68 of passing French. For those who passed French, the probability is 0.95 that she will pass French 102. Will pass both French and French 102. So that's technically this puppy right here, all right? So I'm just going to multiply that 0.68 times that 0.95, okay? So 0.68 times 0.95, and I get 0.646. There is money to send 3 of 9 city council members to a conference in Honolulu. Oh, I need to add one more staplet to the list. One more staplet for the list is counting. So if you look, you'll see counting methods. We'll want this one as well, all right? 3 of 9 city council members. So we got 9 council members, and we're picking 3. To Honolulu. All want to go, so they decide to choose the members to go to the conference by a random process. How many different combinations? They even say the word combinations. They want that one. So the thing is, order doesn't matter with the combination, and they told you combination, so that makes your life even easier right there. And the reason order doesn't matter, you don't care if you're the first or the third person picked to go to Honolulu. You just want to be one of those 3, all right? Then this one's super easy. We'll just do 7 and 4. Make sure we do NPR, and it's 840. And then they do combination 7, 4. It's always smaller. The C one should be smaller. Then we have 8, 8. I can tell you. Oh, this one's a big one, actually. NPR is big. 40,320. And then we have 9, 9. Now I can tell you the answer for this one. In my head, it's 1. Voila. So, oops, I did 0, 0. Helps if you do 9, 9. I still say it's 1. There it is. It's 1. Okay, let's go ahead and submit these. Or do we just have, yeah, let me go ahead and submit. Okay, everybody's right. Let's move on. 5 multiple choice questions on an exam, each with 5 possible answers. Now, this one's a little different. This is fundamental counting principle. So basically, if I were to go, do I have space? I'll go back here. So what we're going to do is we're going to say you have 5 choices for 5 questions, right? So you have 5 times 5, 5 times, pretend I can do times 5, times 5. So that's pretty big. Let's make this bigger. Because you have 5 choices on each question, there are 5 questions, 625. I'm going to guess it's 33,125, but I could be wrong. Let's go ahead and do this. I'm guessing, sort of guessing. 3,125. So if you did 5 to the 5th, or you went 5 times 5 times 5 times 5 times 5, you would get 3,125. So those are the different ways you can do it. Only one of the sets contains all 5 correct answers. If you're guessing so that you're likely to choose same sequence of answers as another, what is the probability of getting all 5 correct? There's only one correct out of 3,125. You just put that in. Don't put in extra numbers. And since that's kind of a hard one, I'll go ahead and submit. Hopefully it'll take my fraction answer just fine. It likes a fraction answer, so do I. Voila, there you go. You just got to remember to divide that 1. To open a combination lock, you turn the dial to the right and stop at a number. Then you turn it to the left and stop at a second number. Finally, you go to the right again, blah, blah, blah. If the dial contains 9 numbers, 0 through 8, determine the number of different combinations possible for the lock. Note the same number can be used consecutively. So I'm going to do how many numbers? For the lock. If it contains 9 numbers, 0 through 8, determine the same number can be used consecutively. Okay, so we only have 3 numbers. So I'm going to do 9 times 9 times 9. So that would be 729. You're like, Mrs. Overman, is it really 729? Let's check it out. 729. It's called mental math. Remember, we were 4th in regionals, alternate to state in this particular category. All right, you have a combination lock. Again, you dial to the right, stop, dial to the left, stop, and do a 3rd number. Now, suppose the 3 numbers of your lock are 2, 9, and 5, but you don't remember in which order. So this one's actually really simpler. How many do you have to choose from for your first choice? 3. You could do 2, you could do 9, and you could do 5. So let's say you pick 2, then you're down to 2 choices, and then you're down to 1 choice. And when you multiply all those out, you don't get 5, you get 6. 3 times 2 times 1 is 6. Submit for testing. And voila. And that's it for part 1 of your review. If you have any questions on any of these and you watch the solution first, that's fine with me. Just make sure you watch it and then you can come by me if you still don't understand it. Good luck on your final.